but
I think
it might
that's
already be
somebody's
recorded.
note taker that's
Okay, the
recording
note
it. So I
taker.
probably don't have access to that one. But
Perfect.
whoever saw it is will have that. He's probably not even here. He's probably having his note taker do it. All right, I'll pass it over to you.
Okay, it says I'm sharing, but I'm not getting the little window, the
I
green
don't
window.
see
So
it.
does anyone see anything?
No.
Good luck. Good luck.
Didn't this just happen to me? Okay.
Maybe you need to
This just
stop it
happened to
and
me on
restart
another
it again.
platform. Yeah, let me try. So now it's really thinking. Okay, let's try this again. Hopefully I don't have to leave the meeting and come back in. Am I frozen? I can't
We can
press
hear,
share
we
now.
can still hear you, but we can't
Oh
see.
no.
I think I
It's
had that issue last week, right? So I have to quit
yeah.
join, right?
Do you want to leave and come
Yeah.
back, maybe like restart it?
I think I might have to leave, but also
Okay.
it's not letting me click the leave button. So
What?
hold on, let
Okay, why
me.
don't I do this? Why don't I try to kick you out?
Okay, yeah, please.
I'll I'll remove you. Oh no, then you can't rejoin.
Okay, wait, I'll force quit and then I'll come
Okay.
back. I'll be
All
right
right.
back.
Okay. Actually, in the meantime, I'm gonna stop.
As you probably saw in the description, it is a beginner level workshop. So if you're here, if you're like just starting to learn, you're in the right spot. I feel myself like I'm just starting to learn about Iceberg. There's plenty to know. So yes, feel free to interrupt me if you have any questions as I'm going. Uh, can you still see my screen? Something just happened. Okay.
Slides. Yeah.
Okay, perfect. So yes, this lab, it's if you attended Yihong's last week, it'll be sort of the same setup. I'll give like a spiel at the beginning, sort of explaining all the technologies that we're going to cover, including Presto, Iceberg. I mean, I have like one slide on MinIO. There's not too much to know about it, luckily. But the workshop piece itself is going to be done on your local machine with Docker. So if you don't want to do it as we go, you're welcome to come back and do it on your own time later and ask questions that come up in our Presto Slack channel for our labs. And I can answer those questions there too. All right. So without further ado, let's go through the why is everything freezing? The agenda here, as I said, we'll cover just sort of what a data lakehouse is, a quick overview of Presto, and then an overview of Apache Iceberg, and then we'll get into the workshop. So, as I've already mentioned, I'm Kirsten. I am an open source developer at IBM, and I currently work on Presto, have for over a year now. It's probably been like a year and a half at this point. But I've also contributed to other open source projects over the last few years, as has my co-presenter slash chat helper today, Yihong. If you want to introduce yourself.
Yeah, my name is Yong Wang. I think, yeah, I work with Kirsten and we work on the Presto community. I think almost 2 years, right? So, yeah, it's a big community and the community is very welcome. So, welcome to join the Slack channel. And if you come to any question, just ask in the Slack channel, or you can create an issue on the GitHub. Yeah, then we can help. Yeah.
Yeah, including like if you have a question today that I can't answer, I'm probably going to send you to the Slack channel and then I'll probably answer you later. So you'll see me around, that's for sure. All right, so to begin, what is a data lakehouse? So to describe what a lakehouse is, I like to describe the two sort of technologies that motivated its creation, I'll say. They're both still relevant technology, like stacks, ways to organize your data. But a data warehouse is kind of the first, traditional, what we think of when we think of data storage, first central data store concept. And a warehouse is pretty much always structured data, meaning, data that's in row and column format. So relational data. By the time it's in the warehouse, it's already gone through the ETL process, meaning it's been, extracted from wherever it lived before, transformed, and loaded into the warehouse. So it's already gone through cleansing, deduplication, format conversion processes, all that. And it's essentially, ready. It's ready as is for analysis. And analysis takes place using, your traditional SQL statements. The downside is, however, it is not very flexible. So it's really difficult to scale, considering the size of the data that we work with nowadays, because not all data is easily, or not only easily, but is possible to transform into that relational structure. So kind of as an answer to the warehouse, the concept of a data lake forms not long after. And it is, its goal is to sort of fix these challenges that a warehouse provides with its lack of flexibility. So with a lake, you are usually storing all types of data. So not just relational data, although you can, but your semi-structured data like JSON documents, your completely unstructured data like images and video, things like that. And, data is usually stored as is. It's kind of just like thrown in there, however it exists. And then, before it's analyzed, it goes through that transformation process. So it's not ETL, but ELT is the order for a data lake. So this is great because it's really easy to scale compared to a data warehouse. But the problem is it can suffer from a lack of quality control because, you're just kind of loading data in there and there's not as much structure to it by design, which is, you might have heard of the term like a data swamp. And that's kind of a lake that's gotten, a little rough for the wear as time has moved forward. So, as an answer to all of those problems combined, the concept of a data lakehouse comes onto the scene. And, it's the same as the other two. It's just an option of how to set up your technologies to store and process data. But, the lakehouse really tries to bring the advantages of a warehouse to the scalable nature of a data lake. And this is where the term lakehouse comes from. It's just a combination of lake and warehouse. Pretty simple. So we can store a diverse range of types of data as we can with the data lake. Usually we're using cloud object storage for that. But at the same time, we have, more control over the data, similar to what we have with the warehouse. So data is often presented in this structured format. You can often query it with SQL, as you can with the warehouse, but you can also do, more advanced processing things that you would usually do with the data lake and at a much higher scale. So how is this done? It really requires a lakehouse setup, really requires two main things. And first is some sort of highly performant processing layer that can be, one or multiple processing engines, depending on your setup. But you're going to need, whatever is processing your data to be really good at it, just due to the, huge nature of the data that you're going to be processing. And second, you will need what's called a table format. And a table format is just a layer of abstraction that sits between the raw storage and the processing layer that, essentially defines how all of the data in your lakehouse is organized and managed. So as with any time we're adding a layer to something, some abstraction level, we get with this a layer of flexibility. And it, really allows us to support those data warehouse features on top of unstructured, lake type storage, such as cloud object storage or HDFS. And an open data lake is just a data lake built on open standards and open source technology. So what's not to like? So here's a little architecture diagram. It's kind of hard to, make a true lake house diagram because, what makes up a lake house is again, can vary wildly depending on your needs. But these are, the basic pieces that essentially will probably show up in pretty much any lake house stack. So at the very bottom is, of course, our storage, our raw data. And as shown, this is usually going to be some kind of object storage or Hadoop HDFS. One layer above this it is admittedly somewhat odd that I'm including this as a layer, but it's kind of to draw a parallel between a file format and a table format to sort of, show you what a table format does. So we know, of course, file formats are a way to take the somewhat unstructured ones and zeros that make up a data file in order to represent them to, both our human brains, but also, different layers up the stack as a single file. A table format does, kind of the same thing. It is, also an abstraction that takes a handful of files and represents them in a more organized form. And in this case, that more organized form is a table. So, these higher layers up the stack, they don't necessarily see individual files, they see a table. And it does so using a extra layer of metadata, which we will see in the next few slides. Of course, one layer up from that is the processing layer. This is fairly self-explanatory, so I won't say much more on that. And finally, at the very top is really an optional layer, but it's however we are going to be organizing our, visualizing our data, whether that's a CLI, which we'll be using today, or something a little more BI related, like Superset, Tableau, or Jupyter Notebook, all that. Plenty of options that can hook into our processing layer. And here, just as the same diagram, these are the technologies we're going to be using today. Again, I mean, file format's not exactly a technology, but you see what I'm getting at here. But again, like you don't have to just have Iceberg, you can have multiple table formats, you can have multiple processing engines, all that good stuff. We'll just work with one of each today to keep it simple. So a little bit about each of these pieces before we get started. MinIO it gets the least love of all of these concepts, but just as a slide for those that are unfamiliar, MinIO is an object storage system, essentially. And, as we know, object storage is a super common format for a data lakehouse, and, a data lake in general, due to its low cost and, unstructured data support, semi-structured data support. There are several, options for storage, object storage. Like usually, in a real life scenario, you're probably going to be working with cloud object storage, but Minio we've chosen here because one, it's free and open source and very easy to set up on our local machines. People do use it in production. That's certainly possible, but it scales down to our level really nicely. And most importantly, as really all S3 object store should, it implements the AWS S3 API, which is great because that means Presto can connect to it as well. So it stores all of its files in buckets, which we will see. It has both a CLI and a UI. We won't be using the CLI, but we will see the UI in our workshop portion. All right, on to Presto, the more important pieces of our lakehouse here. So Presto is, of course, a great lakehouse choice for a handful of reasons. But one, as I mentioned before, it's really built for high performance. We really need a high performance engine in this case. So that works out great. Is there a question? I heard a little noise. Gives me time to put the lip balm on. All right, moving on. So Presto does all of its processing in memory, making it very fast, reducing disk I/O latency. Several, query optimizations are built in, particularly where Iceberg is concerned. So Presto has its own data layout awareness. So does Iceberg. So the combination of the two speeds it up even more. We have optimized efficient stage and task scheduling, resource management options, plenty more. Also, however, is the flexible nature of Presto that makes it really good for a lakehouse. So, Presto, as you might be familiar, has connectors for a handful of data stores, and these would be maybe your more traditional, not exactly warehouse concepts, but traditional data stores like MongoDB, Postgres, that type of thing. But Presto also supports data stored in the lake formats S3 and HDFS through its table format connectors, which are, of course, Iceberg. It also has a Delta Lake connector, a Hoodie connector, and technically Hive, I guess, can also be considered a table format, just maybe a little bit of an outdated table format. So here is a quick Presto architecture diagram. And this, you'll see, the top layer is essentially the same as our lakehouse layer. Middle layer is Presto itself. Here we have a coordinator and 3 workers shown, but this can, scale up to hundreds of workers, multiple coordinators. In our workshop, we're just using a single coordinator that will also act as a worker. And then the bottom 3 layers of the previous diagram are sort of squished into this one bottom layer here. And that is, on the right, your more traditional like data store connectors. And on the left, the table format connectors, which, as you can see, like access the data store under the underlying data store for you. All right, quickly about table formats now. So table formats were essentially an answer to the Hive storage format, which again, like sort of can be considered a table format. If we're thinking of a table format as taking, a bunch of underlying data files and presenting them as a table, Hive certainly did that. The problem developed as we essentially like scaled the amount of data up to what we're using in real life scenarios today. So Hive was great at first, but it started to suffer from these drawbacks, including, really slow reads and writes because the data wasn't exactly laid out in the most optimal way. Things were stored in like a multi-layered directory structure. So every time you went to read data, you had to like look in every single file to see if that was the, information that you were looking for. They also, have no real support for transactions, meaning, you know, for example, if multiple jobs are reading or accessing the data and writing data, incorrect results can be read or written because there's no clear point in time where, data is written and then read afterwards. It just sort of got all jumbled. And there's more reasons than this, but just for the sake of brevity, we'll just leave it at the fact that Hive wasn't cutting it anymore. So the modern concept of a table format came onto the scene. And there are 3 big ones today. Iceberg is definitely at this moment the most popular choice. There's a lot of buzz in the community around Iceberg right now, not just the Presto community, but the data management community in general. But as I mentioned, Presto also supports Apache Hoodie and Delta Lake. They all kind of have their own way of managing the metadata that makes up their tables, which will give you benefits in some places and maybe in a different format would be better for other things. But again, for our purposes and since Presto has great Iceberg support, we've chosen Iceberg for this lab. And this is kind of a visualization about why that is. Iceberg is very feature rich when it comes to, the things that it supports. So Iceberg, of course, supports ACID transactions. So that transaction support that I was just talking about, which, just ensures the highest possible data reliability and integrity, even if multiple people are accessing at once. It also supports time travel, which is the ability to query a table based on its state at a certain point in history. Partition evolution, it has full support for that, and that is where you can change the partition columns for your data over time as it grows or changes. We won't see that in the lab today, but I leave it as an exercise for the workshop taker to, try out some partition evolution if you so choose. And then it also supports schema evolution, which is where you can add, rename, reorder, delete columns from a table over time. We will see that in action today. And then Iceberg also supports all three of the big columnar file formats, Parquet, Orc, and Avro, where as the others, it's only partially support those technologies. So a little more about Iceberg specifically. We already know that it's table format. I think I've driven that point home at this point. But it uses a series of metadata files to keep track of its data. And we'll see this a little more in action, but essentially data is tracked almost on a per file basis, which leads to a lot of efficiency because, we don't have to access a bunch of files to find the data that we need. We just do a few, steps. And then also, we have that support for ACID transactions because every table modification creates a new metadata file that is made current at the moment the transaction is complete. So we can kind of see this in action a little bit with this diagram. If you go to the Iceberg docs, I feel like this is the diagram that's always shown there. But just to explain a little bit what each of these metadata files are, well, we'll start at the bottom layer again because this is very self-explanatory. This is just our data, whether Parquet or Avro. One layer up from that, though, is where things get a little more icebergy. So one layer up is called a manifest file, and a manifest file essentially contains a list of pointers to each of the data files that it is, tasked with keeping track of. It also includes not just the location of those files, but a little bit of, metadata about that data file itself. So that could be, the column bound, so which columns are stored in each of those files, things like that. We'll see a little more about all of this in the workshop. One layer up from this is the manifest list file, also just called the manifest list to keep it slightly simpler. But the manifest list points to a handful of manifest files associated with a snapshot. Snapshot being the state of a table at a given point in time. But again, similar to the manifest file, the manifest list also includes some metadata about each manifest file. So manifest files can be split based on, the partition that they're keeping track of. So if that's the case, the manifest list will, describe the metadata, like which partition is stored, is each manifest file keeping track of. And at the very top is what's called the snapshot file. And this is, of course, what points to the current manifest list. And it also includes some metadata about the table itself, not just not just the table schema, so the columns and, their definitions and their types, but also each snapshot that has, been at some point been the current snapshot of that table. So we can kind of see what happens over time. Say at, time 0, we have snapshot 0. It points to a single manifest list, single manifest file, and just a handful of data. But over time, of course, you're going to want to add data to your table. And, in this diagram, we're sort of seeing now that, not only do we have the information for snapshot 0 still available, but we have created a new snapshot that points to a new manifest list that, not only points to our new data, which is in, yellow and blue here, but also can access our old data, or, prior, what used to be the entirety of our table, in light green on the left, with no need to, rewrite the whole table. You're just reusing the same manifest files and data files, and, able to just add the new data and move on. And as you can see, we still keep track of, the snapshots and the manifest lists that are associated with those snapshots. So you can see how time travel would work in this case. If you want to access the data as it was at snapshot 0, we still have all those pointers intact, and you can, look at the table as though you're looking back in time. And we'll see more of this in the workshop as well. One last thing I wanted to touch on, because some of the terminology, I mean, I feel like happens in every domain, but the terminology can get a bit oversaturated. So wanted to cover the concept of an iceberg catalog, because if you're familiar with Presto, Presto has a concept of a catalog as well. It's a similar concept, but slightly different. So if you hear me use the term catalog today, I almost always will mean the iceberg catalog. I hope it'll be clear which I'm referring to, but feel free to ask if if I'm not being clear as we go through things. But anyway, an iceberg catalog. So we've seen that Iceberg keeps track of all these metadata files, they keep track of other metadata files, but who keeps track of where that first metadata file lives, and that holds all of our snapshots? So this is what the responsibility of the iceberg catalog is. It's essentially doing two things. It's keeping a list of tables and schemas or namespaces, and a pointer to their current metadata file. And it's also responsible for making that atomic swap that enables our ACID transactions, because it is essentially, the source of current truth for each table. So a catalog is, it does require a, I guess, at least in most cases, a separate service. So whether that is the Hive Metastore, which is a popular Iceberg catalog, Nessie, the REST catalog requires setting up a REST server, that type of thing. You essentially need one of these services to do this atomic swapping for you. Now, this exception here is the Hadoop catalog, also called the file catalog, which is not recommended for production, although that hasn't stopped people from using it that way. But for our purposes, we'll be using the REST catalog for this lab. All right. Oh, and I have a slide with a little more information about the REST catalog. All right, this is the last slide. So a little bit about the REST catalog and why I chose it for this lab. Essentially, the REST catalog evolved out of the Iceberg community in an effort to standardize how catalogs are accessed in Iceberg. So with the other catalogs, whether it's the Hive Metastore, Nessie, JDBC, each of them have a module in the Iceberg repository that has to be maintained, and they have to manage all the integrations for all of the different data sources and things like that. The REST catalog evolved to try to make it a bit easier on the maintainers of Iceberg that way. So the REST catalog is essentially just a specification. It defines the common API that all catalogs will use. But as always, when we're adding, again, it's kind of a layer of abstraction. It also enables a lot of new features that are not available in other catalogs. So, we're separating the ability to do a lot of the traditional Iceberg catalog things like creating tables and putting data into them. We of course still have that ability. That's sort of the bare minimum for what a catalog has to support. But with the REST catalog, you can kind of just plug in any other underlying catalog features that you might want to support. But as long as they speak this REST language, this REST API, they, you're considered a valid catalog in Iceberg's eyes. So the community is really prioritizing the REST catalog. It's certainly prioritizing it for new features, but they're heavily suggesting that the community move this way because of all these extra features that it provides, including OAuth 2 support and these more important things that become more relevant. So I think they're on version 2. Version 3 is on active development. The difficult part about the REST catalog, if you're implementing it for your own use case, is you have to stand up a REST server that speaks this REST API. For our purposes, we are using a really simple Docker image that was originally built at Tabular. But essentially, under the REST server hood is a JDBC catalog that does all of our, that's responsible for the atomic swap and all that good stuff. Okay, I am finished with just the talking part of that. I will now end the show. I'll copy and paste this link so I can find my windows. So here's the link to the lab. Like I said, and as you'll see, it's in a GitHub repository, a public GitHub repository, so you can come back to it whenever you want and go through the steps on your machine. Like if you don't have Docker installed right now, no worries, you can just install it later and do the lab on your own time. I will still be available to answer questions, but if you open this link, you'll see, you might not see this exact page. You'll want to navigate to, I believe, the prerequisite step here is our first step. And I might run the commands with you, but unfortunately I have more talking to do. Hopefully you're not sick of me. And I hope I don't run out of time. But essentially your first step is you're going to want to clone this repository. This is where all the code lives for, the Docker compose file that we're going to use. And you want to change into the directory you just cloned, of course. And from there, we can move to lab 1.
Can I have a question before to go
Yes,
to
definitely.
Yes, please. I think you cover a lot of things here related to the Presto and the connector for the different storage solutions as well as the table format. What about Apache Ozone? Because it is also like object storage, similar to be like S3 bucket or NIO, something like that.
That's a good question. And I really don't have the answer. I've heard of Ozone, but admittedly never really looked into it. Actually, let me note that down in my ongoing
Sure.
things to look into folder. But no, I really don't know much about Ozone. Yihong, do you have any
No.
It
experience
is
with it?
object store. similar to the MinIO and S3 bucket of AWS.
I would assume so.
Apache,
I mean,
Apache Iceberg.
assuming it supports the S3 API. I mean, I would be shocked if it didn't, if any S3 storage didn't. But anything that supports the S3 API should be good to go. You know, if you're wanting to use that and try it out on your own, it should work. MinIO was really just my choice because I'm more familiar with it. I had used it previously, so that's what I selected. But yeah, I don't think there's any reason Ozone shouldn't work, and I'll probably look into it and see if it's worth, updating the lab if it has any, distinguishing features that we could highlight. Let me make a note of that. I don't know if that's helpful at all, but
Maybe I
it's
can
kind of a
expect you to come back later, maybe, or anytime.
perfect. Yeah. Yeah. And also feel free to ask in the Slack channel. I'll probably still answer you, but it could be good for people just in the community to know that there's interest in Ozone.
Yeah. And also, because there is another object store also preferred in the market, like Google Bucket, Azure, similar to the
Hmm.
AWS S3 bucket. So is there any possibility also to have that connector to Presto?
Yes, definitely. I've only tested, but sometimes I'll do things with AWS. Uh, and yeah, it works fine. I think Google Cloud specifically, there might be some bugs, um, and some work that's being done on. I might be making that up. But I seem to remember that there might have been a bug or two. But yeah, every other, like, I've used IBM Cloud to test it, just as long as the S3 API is implemented, should be no problem at all. But like I said, I just chose MinIO because it's free and pretty lightweight. And Abbas, I think I see a hand raised at least. This window
Yeah,
is tiny.
I just want to. So I've worked with the Hive Metastore before, and I'm a little confused as to how the Iceberg catalog would integrate with the Hive Metastore, because I guess the Hive Metastore is just about a bunch of tables storing the metadata in it. So then, if Iceberg is not a bunch of tables storing the metadata in it, then how would the Iceberg catalog integrate with Hive Metastore? So that's a little confusing.
So it does get confusing too, like you're not alone in that because again, like all these terms it's kind of trample over each other. But really, so since Iceberg, you can use the Hive Metastore as an Iceberg catalog. So it's a pretty common use case, in fact, for someone to, have started with Hive Metastore and Hive and to essentially like migrate those tables to Iceberg. And what happens when you do that is essentially uh, Iceberg just sits like on top of Hive. Like, so as we'll see in the lab portion, these metadata files that Iceberg holds on a table, it'll go through your existing like Hive table as stored by the metastore and kind of like translate what Hive keeps into, what Iceberg expects. Um, so essentially, you don't really have to do a ton of work yourself. The Iceberg library takes care of it for you. I will say a caveat on that is Presto doesn't have a direct migrate command yet for converting like a table stored in Hive with Hive Metastore to Iceberg catalog, using Hive Metastore as a catalog. But that's a very common transition to make. And the Iceberg library itself. Like the code is highly, I'll say, like biased towards people in that scenario, because Hive Metastore is, I would say, the most popular catalog to use because, you know, essentially of this exact scenario. A lot of people already used it. It was just the easiest thing to make the transition. So I don't know if I kind of rambled there. I don't know if I answered your question.
Can I help a little bit?
Sorry.
Can I help a little bit?
Yes, please.
Yeah, I think Hive Metastore will be in the top. It will tell where is the table locations, even if it is Iceberg or other external table like Parquet or other table format.
Right.
Then you get the location of the table, where is the table. Then the rest of the schema and the metadata will be taken from Iceberg metadata.
Yes. Yeah, that's a good clarification because, and you're right, the Metastore is still on the top because also it's the Iceberg catalog that's used. And then you're right, like from there, you know, the format underneath is Iceberg, but the original file structure is Hive. So yeah, there's a lot of interweaving going on here.
Yeah, but I think what you mentioned was that the table format is separate from the catalog. So then what I understood was that the Iceberg catalog was like a replacement of some sort for the Hive Metastore, which is also a catalog in a way. So if I did I catch you right or wrong? I don't know, but you said that Hive
Yep.
Metastore is like a facade on top of the Iceberg catalog, or is it like a way to access the Iceberg catalog, or like I don't know. Am I confusing
Right.
myself or?
No. I mean, I think this might help, this piece of information that I have neglected to mention until now. So Iceberg, really at the heart of it, is just, you know, kind of a way of doing things. It's simply like a spec of like, okay, if I am using, like, no matter what catalog I'm using to keep track of that location of my data, you know, this is how the data is going to be laid out. You know, we're going to have this series of metadata files and, you know, all of that. Iceberg itself doesn't do very much action, you know, outside of manipulating its own metadata files. What really is doing a lot of the work is the catalog implementation, which, you know, if that's Hive Metastore, you know, you're going to go through Hive Metastore into Iceberg. Iceberg's going to update all of its, you know, specific files the way that they need to be updated. But what actually does the data manipulation is, you know, Iceberg doesn't really care. It's really just a definition of how things are going to be laid out, that the catalog takes care of the actual implementation of, you know, how the data is, when the data is manipulated and inserted into and whatnot. Like the table format concept, you know, like I mentioned, Hive is that as well. It's just a way to organize the data. As far as the actions that are done, like Iceberg isn't really a service, so it's not doing much. It's just defining your, you know, your layout. And again, I don't know if that's helpful either. It's all very, it's very convoluted. So I apologize if I'm not explaining it properly.
I can chime in here a bit.
Yes.
Recently, I have been working on this format. So the thing is, like, Iceberg catalog is just a meta store. Like, you can, let's say, like, we have tables in Iceberg, and to insert or to ingest data into those tables, we use Spark. And then while creating the Spark session, we are actually using a function called enable Hive support, which means like you can actually use Hive as, you know, meta store. Like like both can be interchanged, or like Iceberg catalog will work with Hive Metastore, if that helps. So end of the day, either I, whether it is a catalog or Hive Metastore, it is just a place to store your metadata. End of the day, you have to store your files, your data in any of the S3 buckets or any of the storage platform, and you have to have a specific format to store. And these uh, metastores have those information where the file is exactly located, how that file is being partitioned. Like if it is partitioned, like you create multiple subfiles, right? As shown in earlier slides. So these metastores have that information in them. Yeah. If that helps.
Yeah, it's a very
Yeah,
complex
it's
concept
exactly. Yeah.
yeah, and I wish I had to myself do a lot of diving into this too, because I don't find that Iceberg's documentation on this is quite what I would like it to be, at least when I was first learning. But yeah, your catalog, you can change out, if you're using Hive Metastore and then you decide, oh, I want to use REST instead. Yeah, like that doesn't really matter as far as Iceberg's concerned.
Yeah, and even even the Metastore have their own format of storing the files. Like they have their own formats. So if your Metastore layer supports that specific format, I think we can use any catalog we want. At least that's what my understanding was so far.
Yes, yeah. I mean, yeah, I would agree that that's correct. I'm sure there's a few caveats, but for
Yeah.
understanding purposes, definitely that's also my
Yeah.
understanding. So I'm also, please, if that isn't enough, I'm not just saying this, like, please ask in the Slack and I will continue to answer like whatever questions that might help you understand it better. Happy to like continue that conversation for as long as we want. Because I know I'm not exactly doing it justice here. All right, so I know we're getting to the end of our time, or are we? Are we? Oh no, we still have 30 minutes. Okay, we can probably knock this out in 30 minutes. But again, no worries if we don't. I'd like to think the instructions are easy enough to follow that you'll be able to, do so on your own time if you'd like to. So if you have the repo cloned and you've changed into that repo, I don't think I have this listed here, so I'm directly contradicting what I just said about it being easy to follow along. But you also want to then change into the conf folder, CONF. And this is kind of like the outline of the repo. I have it open in VS Code. So change into that conf folder because that's where we're going to start up all of our Docker containers. So we're using Docker Compose just because it's a really easy way to start up multiple containers and connect them and have them talk to each other all on the same network. So it's really just like a shortcut. You could set up all these containers manually if you wanted, but this makes it a little easier. So we run Docker Compose up -d, and you should see, a bunch of containers start up. I think we have something in the realm of 5 containers and a few volumes that will be created. I can probably just go ahead and do that so I can confirm. Maybe not. Okay. So yeah, you'll have, a bunch of, 5 containers, a few volumes, and a network on which all of our containers will be talking to each other. So, Docker immediately comes back and says like started, but under the hood, some of these containers take a little bit to actually start up. particularly the Presto image and the Presto server, which is quite large. The image is quite large, so it might take a while to pull. I already had it pulled here, so I don't have any additional output there. But while that's pulling and while the container is starting, I will go ahead and cover some of the setup information, just in case, you come back to this later and you're wondering what all these different pieces of our Docker Compose file are. So quickly to go through each of them, each of our containers themselves are going to be services. So the first service here is our processing layer, which of course is Presto. It's named Presto Coordinator, but it will be performing the duties of a worker as well. So essentially what we are doing here is, specifying which image we want to pull, specifying that we want all of the things in this local Presto, etc. directory to be mapped into that coordinator container. And this is these are, as you can see, all the catalogs, the configuration properties for all of our catalogs, the Presto catalogs, not Iceberg catalogs. So, the TPCDS catalog and all of these built-in Presto catalogs. And we also have a configuration.properties file for our Presto node. And here, as you can see, specifying that this node is a coordinator, we want it to do work, and we want it to be on this port. And the URI, where if we had them, workers would be used or would be registering themselves with. We do not have them, however, but we'll see in the UI later if we want. So we'll access it with that port mapping here. This is again if you already have something running on your local host port 8080, you might want to change this left-hand version. So if you want to use a different local host port, you don't have to. The only reason we would be needing this port at all is if you do want to look at the Presto UI to see, the queries that are submitted, but we really don't have a designated place where we do that. So that is really not a mandatory step. We also have our REST server as a separate container. So this, as I mentioned, is the Docker file that was written by Tabular. And it's really just like a small shell wrapper around what is actually under the hood a JDBC catalog. So we've specified this, wish that would stop. This catalog URI, these are all properties. If you wanted to dive into the code, which is open source, of course, for this REST server image, it becomes quite obvious what it's doing under the hood. And that might be useful if anyone's particularly interested in the REST catalog and how it works. I would suggest doing that because it's helpful to see what's going on there. So I won't belabor that portion too much, but I will say that we also need this Postgres container. This is, as I mentioned, what is just going to be our underlying catalog. So all it's going to do is store, this would be like the, underlying storage that's going to give our table name and the pointer to where the current metadata file is. And for all of these, we have various environment variables that are connecting, all of them need different, usernames and have different authentication mechanisms. So you are welcome to look through those for more details, but you can also take it for granted that it's all been set up for you. MinIO, as mentioned, so MinIO actually has two services here. MC is actually just doing some setup for us in the background. So it's essentially creating a bucket for us in our S3 storage that's going to be called warehouse, and then it really just quits. MinIO is the more interesting service of these two, because this is what we will actually be looking at the UI for. We'll be able to see all of the changes to the data that we make in the MinIO UI if we want to, as well as all the changes to the metadata, things like that. All of that will be stored in our MinIO S3 storage. And again, feel free to, if you want, change these ports. I know 8443 is a weird one. So if you want to change 8443 to 9091 or whatever to make it a little easier to remember, feel free to do that. But we will be accessing the MinIO console. So, choose a port that you like. And if you do change any of the ports, you're going to have to rerun the docker compose up command so that the new system is set up properly. All right, there's plenty more I could say, and as I scroll through this, something might catch my eye that I will feel the need to explain. Also, feel free to read through all of this on your own time. It's essentially what I'm saying out loud right now, but maybe a little more easy to follow if you're reading it, as opposed to just trying to listen to me. But at the very end, you should have, essentially an output that looks similar to this, that all of your containers are running, your volumes created, and all that good stuff. And we'll check now just to make sure that everything set up properly. So you can run a Docker logs command to on the MinIO service. If you do that, you should see, output. You'll see a few things in the logs, but what we are really looking for is, this output here that I've highlighted, which confirms essentially that setup went as expected. The Iceberg one will be particularly important because there is occasionally a race condition that happens. It shouldn't happen this way, but essentially our Postgres container needs to start up before Iceberg REST server container starts up. It doesn't always happen that way. So if you run, in fact, yeah, here I have an example. If you run this log command on the Iceberg REST container and you see this error output, just do a Docker restart Iceberg REST. And then once it shouldn't take very long. It's a pretty small container, but you should see, which luckily I do, that this time it went fine since the Postgres container is already up and running. So you might have to do that. I should probably put that in more specific information about that into this document. So I will do that sometime today. And then finally, the Presto coordinator is the last one that we kind of want to check. And what you really want to see is just this server started output as the very last line. And again, if you don't, just do Docker restart Presto-coordinator and everything should work the second time. This is the point also where if you wanted to, you can open the Presto UI and see that you have one active worker registered. If your Presto server isn't ready yet, you won't be able to see the UI. So it's just another way to confirm that Presto is up and running. Okay. So one last thing I wanted to touch on specifically before we actually start doing interesting stuff is how Presto connects to Iceberg specifically. So as I had in that diagram from the slides, we really have if you're familiar with Presto and Presto connectors, you might have seen, particularly in the lab last week, you might have a MongoDB.properties or a MySQL.properties that tells Presto how to connect to, the database that we want to connect to, say it's MySQL. It is the same concept if you're using a table format connector. So, Iceberg is no exception here. We really just have a properties file in the location that Presto expects to find these such files when it starts up. And we define a few things here. So, you know, the connector name is of course Iceberg. It will always be Iceberg if we're wanting to use Iceberg. And then we are specifying the Iceberg catalog type, which in our case is REST. This could also, as we've mentioned, be Hive for Hive Metastore. It could be Nessie. It could be, you know, Hadoop if you're using the Hadoop catalog. But, you know, the rest of these become a little more self-explanatory. This is the URI that our REST server is living at. Presto needs to know where that is so that it can access that information. We also have the path to our warehouse in S3, which we will see in action in MinIO in a bit. And then, confusingly, some of these properties are prefixed by Hive. This is kind of a legacy thing. So this doesn't do my explanation from earlier any favors, you know, with the Hive Metastore versus Hive versus which Iceberg catalog is which. But all you really need to know about these properties are, these are just the properties that we need to specify to Presto to connect to S3. Hive isn't involved. It's just a legacy naming system for connecting to S3. So we do need to give Presto the S3 endpoint so it knows where our data is living at, as well as the username and password. And we want to specify that we're using path style access instead of dot notation to access our endpoints here. And essentially that's it. If you do that, and you know all the properties have the correct value, that's all you need for Presto to connect to Iceberg. You don't have to download anything or do anything additional. With the caveat, again, of the fact that whatever you're using as your Iceberg catalog is a separate service that you have to set up separately. And then once that's set up, just supply the relevant information to Presto in this properties file, and you know, that's it. Nothing else required. You can use Iceberg. You can start using Iceberg right away in Presto. Okay. So hopefully I've talked enough and everyone is set up. We can move into lab 2, which is even less interesting than lab 1. Lab 2, we're really just checking to make sure that our S3 storage got set up appropriately. So, you know, I guess this is also kind of an alternative to the Docker logs command for MinIO for our S3 storage. But if you navigate to localhost, if you didn't change the port forwarding address, it will be port 8443. You'll be prompted to log in. Sorry, mine's really tiny. I thought if I just kept, okay, there. And what you should see when you log in, it's MinIO and MinIO123 are the username and password, all lowercase. When you log in, you should see here a single bucket called warehouse. Nothing is in it because all our MC service did was create this warehouse bucket and quit. But if you don't have it, it's not that big of a deal. You can essentially just create the bucket yourself. So you'd see a page that looks, well, that's not doing much. The page that looks like this with an empty bucket, just create a bucket, name it warehouse for convenience, because we've already defined in a few places that this is the location of our warehouse. So it's just easier to name it warehouse so that you don't have to change the Presto properties file and restart Presto. Okay, now we can actually start doing things. I suppose with 15 minutes, if anyone has any issues at this point, please feel free to let me know. Because yeah, this next part will be more of the interesting stuff. All right. Okay, well, in that case, let's move forward then. So to start, really from this point forward, everything we're going to be doing is going to be in the Presto coordinator or CLI. So, well, both, I guess. So we're going to exec into our Presto coordinator container and start the Presto CLI with this command. When you do so, you should get the Presto CLI notation here, signifying that everything went fine. And just for a sanity check, if you'd like, you can run this show catalogs command. Again, these are Presto catalogs, not exactly Iceberg catalogs, but you should see this list of them. Of course, the one that we're really concerned about is Iceberg. We won't be using any of the other ones. So as long as Iceberg is there, you're good. Okay, now it's time to create a schema. So what we're doing here is just like any, create schema SQL statement. We are going to create a schema. What differs maybe from your traditional create schema sequence, if you're not used to working with, S3 storage or data lake storage, is we're supplying the location of where this schema is being created, which again is just going to be our warehouse bucket of our S3 storage, which Presto already knows how to connect to based on the information in the properties file. And then go ahead just for simplicity and run this use statement. This is just specifying that we want to, all of our future commands, unless otherwise stated, we want to use the Iceberg Presto catalog with the min.io schema that we just created, so that we don't have to, for every command, specify, the fully qualified name of the tables we'll be creating. Okay, so we can finally do something that will actually create, it won't create any data, as we'll see, but it will create metadata. So, we're just doing a create table statement where, as you can see, we're not creating table as, we're not inserting data into that table yet. We're just defining the table's schema, meaning it's, all of its columns and the column names and IDs. And again, specifying this location. You don't really have to specify this, but it makes it a little easier for human brains to understand where our data is going to be located when we run this statement. Okay, so if that went well, if you navigate back to your min.io console, you can refresh. You can see, as we specified, that we do have a min.io folder here. It's not exactly a folder, but just for our purposes, we'll call it that. And we have a books folder, which is, of course, the name of the table that we just created. So in here, we have a metadata folder, but no data folder. And this kind of makes sense if you think about it. I mean, we didn't do anything with data. We just defined the table. And this folder is, created by the Iceberg spec as, as defined when you're creating a table. And this, let me expand this. As you can see, is only a metadata.json file. It is that top layer of the iceberg, that iceberg of, metadata files. It's just the top layer that essentially, lists the snapshot and the table definition. So if you do want to download this, unfortunately, min.io tricks you and says, oh, you can preview this file. No, it won't let you, but you can download it and see what's in there. And I recommend, you do if you're really interested in how the internals of Iceberg works, because it gets really interesting, just sort of seeing what exactly is changing every time you make a change to the table. But yeah, for now we have, as you can see, just this metadata file. We don't need a manifest list because we have no data to point to. We don't need a manifest file because we have no data to point to. And we obviously don't have any data files. So let's create.
I muted that.
Okay. So let's go ahead and create some data files. So that'll be with this command, we're just going to insert three rows, you could call them, into our table. Just the names and authors of various books here. And if you'd like, you can, verify that that all went off without a hitch. You'll see a table that looks like this, exactly like this, ideally. And now, if we go back to our MinIO console, we have a few things that changed. So I'm still in the metadata folder here. As you can see, we have a new metadata.json folder, file, which makes sense because we now have a new snapshot. Anytime you add data, do any operation on data, delete data, insert it, upsert, anything that actually acts on the data, you will create a new snapshot file with this metadata.json, whatever the postfix, I guess. And then we also have here our manifest list, which has this snap prefix, and our manifest file. We only have one of each because the amount of data we added was so small. In a real life scenario, this operation might create multiple, but for our purposes, very little data. So no need to have more than one of each file. And then similarly, co-located with our metadata folder is the data folder. And this is, again, just the Iceberg way of doing things. The Iceberg spec will by default have both the metadata folder and a data folder co-located. They don't have to be. You can configure that to be something else if you want to. But from scratch, that will be the default. And we have one single Parquet file. Again, we only need the one file because it's such a small amount of data. But of course, you might have more in a real use case. So now from Presto, we can do some interesting queries now that we have data in our table. So Presto has this concept of hidden tables for Iceberg, where you can essentially query the snapshot tables, the manifest list tables, the manifest file tables, all of that. And you can query it with these special commands called hidden tables. You'll just use this $sign notation and make sure you have everything in quotes. It's easiest just to copy paste, of course. But you will see that we have one snapshot. The parent ID is null because it's the first snapshot. It has no parent, and it's current. It's the current snapshot. Similarly, there is a snapshots hidden table that you can query. It has very similar info to the history table. The history table is a little more like I don't know, just a minimized version of the snapshot table in some ways, because you can see in the snapshots table, we actually have the pointer to the manifest list that's associated with this current snapshot. And, if you cross-reference, obviously this is not going to be the exact file name in this case, because it, comes up with new unique IDs every time. But if you cross-reference your output, it will, of course, match with what's in your MinIO. And as mentioned, we also have some metadata that's associated with this manifest list. So it's not going to be very interesting, again, because of the small amount of data that we have, but it should, show you at a glance that we added a single data file, which we've already verified to be true. It's 3 records, which we know to be true, the size of those files that were added, and anything else Iceberg might use in order to essentially fast track itself to the correct data when we're making queries on that data. We also have a hidden manifests table. So this is just the, as you can see, it's the manifest list, the contents of the manifest list. And again, we just have in this manifest list, it's only pointing to a single manifest file. This is its name. And it also has some metadata about that manifest file, the snapshot it's associated with, as well as, some of the things that we've already seen, how many data files were added, the partitions. We're not working with partitioning in this workshop, but, if you were, you would see which partitions are associated with this manifest file. And lastly, the files hidden table. Again, fairly self-explanatory. It's the output of the, each manifest file. And as we can see, it points to the actual raw data, as well as the format of the data, as promised, the column bounds, so which columns are stored in this file. Again, it's all of them in our case because there's no need to split our data up into columnar, different columnar files. It's just a tiny amount of data, but yeah, you can see we have a lot of data in here that, Iceberg and Presto can use to sort of fast track their way to the underlying data. Oh man, I'm really running out of time here. Also, feel free to skip ahead if you don't want to listen to me talking. But our next operation is schema evolution. So we're going to add a column to our table. And again, after like every operation you do, if you're really curious about what Iceberg is doing, you can go in, see what changed in the file. In this case, we have a new metadata.json file. But again, note that we don't have any new manifest list or manifest files. The reason being, again, that this alter table statement has really nothing to do with the data yet. It's just an alteration to the table definition. So the only thing that changes in this case is that snapshot file, that metadata.json file. When we do insert data, however, that is when we will see the new snapshot, not only a new snapshot file, but also the new manifest list and the new manifest file. And again, you can check via min.io. You can also check using the hidden tables. The hidden tables, I think, lay out this information in a easier to consume way. So, as you can see in the snapshot query, we now have two snapshots. One is our previous one is our current one, and it tells you what manifest list is associated with each of those files, as well as, in this example, we've added only one record, which is accurate, and yeah, it all checks out. So again, a snapshot is only created when you do an operation on the data. If you're doing some table definition change, nothing will really change until, snapshot-wise, until a data operation is performed on top of it. And last but not least, we'll do a few time travel commands. So again, time travel just lets us see the state of a table from some point in the past. So in this example, say we added one record in the last, query that we ran. Say we don't want that anymore. I mean, this isn't exactly a real life, not exactly true to a real life scenario, but say, hey, we don't want that record in there anymore for whatever reason. I'd like to see what the table looked like before that was added. This would make much more sense if we had more than 4 rows to our table. But you can do so using, so first, you can either run just a vanilla select all from books, the snapshot hidden table, or you can run this full command to get an abbreviated version. But what you want to do is copy the previous snapshot ID. And then you can run a select statement and add the qualifier for version as, and then paste whatever snapshot ID is your previous or your first 0th snapshot ID. And as you can see, we have only 3 rows in this version. How? Again, it's because when we're going through and completing the query, Iceberg tells us, okay, rather than looking at the second manifest file we created, we're just going to look at that first manifest file that was created, because that is only responsible for the data that was available in that table from that point in time. And you can do the same type of query from a timestamp. So if you don't have the snapshot off the top of your head, you can just use a full timestamp, same results. And lastly, Iceberg does have a procedure where you can roll back to a previous snapshot. So if you want to make that query permanent, essentially, like we permanently only want to see the data that was available in the previous snapshot, the procedure rollback to snapshot is what you use. This has a slightly different syntax than the other SQL commands, as you can tell, but so, we're running it on the iceberg.system schema instead of the iceberg.minio schema, but you supply minio as the schema, books as the table, and then the snapshot ID of, whichever snapshot you want to roll back to. And now, if you do a select statement, you'll see that row 4 that we added in snapshot 1 is no longer considered as part of the data. And you can check out, all of the different how all the files have changed and the hidden tables have changed. But also, as you can see, any operation you do to the table definition is not, you can't roll those back. It's only data operations that will be rolled back. So, the column we added, even though we added it, maybe you could consider, like, before we, wanted to do something more interesting with the data, it's still going to be there. That's just a design decision based on, it's an Iceberg design decision, essentially. It's for security purposes. So if you have any other questions about that, I'm happy to answer them either now or in the Slack channel, whenever. But that is the end of the lab. Sorry that I had to rush that last part. I do a lot of talking. But I am personally available to stay on for questions, or as I mentioned, feel free to, ping me on Slack.
Well, thank you, Kirsten. That was a ton of content. So I hope people were able to, did anybody make it through all the way? Just maybe a show of hands, or you can type it in. Hopefully somebody did. Oh, Saad's note taker doesn't like it. All right, cool. Well, we'll send out the recording after this. I'm gonna stop the recording now.